Well, good afternoon. My name is Anetter, and I'm doing my best to try to explain the derivation of the Michaelis-Menten equation. Uh, Up front, I'll probably be looking down, kind of looking at my notes and writing at the same time to explain. So I'm gonna try to do the best to explain it to the best of my ability. So as I explained, I'll be explaining the Michaelis-Menten equation. The Michaelis-Menten equation describes the variation of the enzyme activity as a function of substrate concentration. So basically, the first step is we'll start off with the kinetic enzyme kinetic, that is a specific enzyme substrate complex, which is we'll look at the proposed model for the enzyme substrate complex. So to start off with step one, we would look at the the enzyme plus substrate. Yes, two. Okay. So hope that looks right. Sorry, I don't have a whiteboard. You can see that. Might be backwards. That's how you see it. So basically, you have the enzyme plus the substrate. So if you go forward, you have K1, which goes to the enzyme substrate complex. Now, if you were to go in reverse, you would have your constant would be uh, K with the -1. Now, as you move forward, you have K2, which when the enzyme substrate disassociates, and then you create, you'll just have the enzyme, and then you'll have the product. So that's step one. Now you want to look at the rate formation, which is basically kind of the enzyme substrate. Then you want to look at the constant, so you will break it down as to the enzyme substrate plus equals the constant K1 times the enzyme and the substrate. So you have ES equals E and then S, or K1 times S. So that's how you would see that in step two. Now you want to look at the rate of the breakdown of ES, which is step three, which, which is ES, which is the enzyme substrate, is equal to K1 plus, or let's take that back, equals to K1. It can be written in different ways, but you can do ES, which is the enzyme substrate, plus K2 ES, which is, as I stated, which is the rate breakdown. Okay, now let's move on to step four, which is kind of gets a little messy. So you want to go into the steady state assumption. Okay, so the steady state assumption is the concentration of intermediates, in this case, which is the enzyme substrate, stays the same even if the concentration of the material and the products are starting to change. So you want to look at step four. So in this one, you have, which it can get kind of funky, but I'm gonna break it down, I'm gonna simplify it and make it one step. You have the enzyme and the substrate over the ES complex, which is equal to K1 negative, which is the constant, plus K2. Remember that when that moved forward to make the enzyme and the product, over K1. Now, in this instance, the second half of the equation, which is K1 plus K2 over K1, is actually the Michaelis constant. Is actually the Michaelis constant. You can see that part. Okay. So now let's go even further. with the Michaelis constants. So now we can kind of simplify that even more, which is the enzyme substrate over the enzyme times the substrate is equal to the Michaelis constant in the next step. Okay, so now I need another sheet of paper because it can go in so many ways for this one. So let's go to step 6. So go to step 6. You can do, so now you have the E total, which is everything, the enzyme, the substrate plus the enzyme complex. So you have E total equals, no, I'm sorry, take that back. You have the enzyme substrate equals E total, which is everything, like I said, E total minus the enzyme substrate, which you do the enzyme substrate times the substrate over Kn. But then that goes into, once you simplify that, goes to Es, which is the enzyme substrate, equals E total over, oh, take it back. Let's do this again. Let's try to make it look right. So go E total, then you have the substrate over the substrate plus the Michaelis constant. Okay, now we're kind of coming to the end, so we have step 7. Okay, so now we're getting towards the end. Okay, so we're going to have the velocity. We're looking at the velocity, which is V naught. So we have V equals K2. Let's get started. No, because then now we're simplifying. So V equals K2 over times E total. Then we have the substrate over the substrate plus the Michaelis constant. Okay, so now we're getting close to the V max. So in this situation, V max is equal to K2 times E total, which is the total enzyme. So that's this part of the equation. So see how we started off with the E total portion? Now you have, this is the V max, because V max equals K2 times E total. So finally, we get to the final step of the variation of derivation of the Michaelis-Menten equation. So last step, you have V naught, which is the initial velocity, equals V max, because you have the K2 times the E2, which is basically V max, over the substrate, with the substrate divided by the substrate, plus the Michaelis constant. So once a enzyme has reached its Vmax, basically it's saying that all enzymes, all active sites of the enzyme are full. Basically, they're saturated and they've reached their maximum potential. So once you get to Vmax, you kind of plateau. So if you look at the graph, create a graph, and it goes up, but then it kind of plateaus out, basically, this is where an enzyme has reached its Vmax. So once an enzyme is kind of linear, but then it kind of plateaus out, that's where the enzyme has reached its Vmax. So all of the active sites are full, the enzyme is saturated, and the enzyme has reached its maximum. So I hope I didn't ramble on. I hope I was able to explain thoroughly the derivation of the Michaelis-Menten equation. And thank you for listening.